Hello everyone, in this video I will discuss Staudinger reactions, its important features, mechanism, applications and also problems. So let's start. Here we have the starting material which is organic azide. So in organic azide we will have the azide group which is N3, and what product we are getting? We are getting primary amine. So here N3 group is the synthon for NH2. From the color you can understand that out of this 3 nitrogen, 2 nitrogen will be removed as nitrogen gas, and the fate of PPH3 which we are using in the first step, that will be converted to triphenyl phosphine oxide, which is stable because of this P double bond O. So this nitrogen gas formation and this type of stable compound formation, it can facilitate the reaction. Fine. Now here first step is we are using PPH3, second step is hydrolysis of the intermediate, which you can see here. The intermediate is iminophosphorane, which is nitrogen phosphorus ylide. This type of ylide you have seen in Wittig reaction. So this intermediate will be formed first in presence of PPH3, and then when we will hydrolyze it, it will be finally converted to primary amine. Now this reaction is a mild azide reduction because ultimately it is reduction of this N3 group, and it can tolerate other functional groups. So suppose you have double bond in this R part, that will be tolerated. And this azide you can easily prepare via simple SN2 reaction. So suppose you have taken Rx, suppose RBr, and that you can convert to RN3. Also you can apply Mitsunobu reaction, which I have already discussed. For Mitsunobu reaction, how you can prepare by this reaction the starting material for Staudinger reaction. For that you can click on the link right now appearing on the screen. Next we will see what is the mechanism of this reaction. So here we have the first step where the reaction is between this organic azide and PPH3, and in this step this iminophosphorane intermediate will be produced. So first here we have written this azide in this way, Rn minus then N plus triple bond N. Now you can also write this intermediate in this way, that is also fine. So in this case negative charge will be here. So the way I have written in the black color, in that case the attack will be on this nitrogen and the middle nitrogen will be neutral. But if you are drawing the second one, in that case the attack will be towards this nitrogen. Again this middle nitrogen, it will be neutral. Now if you follow the previous one, in that case this type of phosphazide will be produced. But suppose if you are following the second one, in that case there will be NPPH3 plus then N double bond N minus, and in that case this negative charge will be attacking this one. But in our case we are attacking like this. But whatever way you follow, ultimately you will reach the same type of ring formation which you can see here, 4-member ring formation. Now this type of ring is obviously not very stable, so finally it will be decomposed, and after this ring decomposition there will be removal of this these 2 nitrogen in this way. So see, NP double bond formation and NN triple bond formation. So this is nitrogen gas, and this type of nitrogen gas, whenever there is some stable molecule is removed, in especially it is gas, so this is thermodynamically very stable. So that is the driving force for this step. So here we have obtained the intermediate iminophosphorane. In the next step, hydrolysis of this iminophosphorane. So water molecule, it will attack here and negative charge will be over nitrogen. Now this oxygen which is positively charged, this hydrogen minus H plus plus H plus. So proton will be transferred from oxygen to nitrogen. Now it will be converted to a neutral molecule. And finally there will be oxygen phosphorus bond formation. P double bond O is one of the strongest bond in organic chemistry. So that is why this molecule is very stable. And this hydrogen, that will be now to this nitrogen. Fine. So negative charge will be over this nitrogen and this proton will come to nitrogen, and finally we will get RNH2, and this is the byproduct. Okay, stable byproduct which is also helping us to move the to shift the equilibrium towards right hand side. Fine. So these are the 2 important steps for Staudinger reaction. Next we will see what can be the different types of variation for this Staudinger reaction, or you can say other product possibilities from the iminophosphorane. So see, at the middle point you can see the iminophosphorane. Now I will request you, don't just randomly look at any molecule, just follow my cursor. Okay. So if you look at this part, it is the normal Staudinger reaction that we have just seen. How you hydrolyze the iminophosphorant and you get RNH2. So in this case, water molecule is basically acting as nucleophile because it is attacking the phosphorus of PPH3. But if you use different types of electrophiles, such as we have used here acetone, that is ketone, or you can use CO2, CS2. So in that case, if you write the iminophosphorant, its resonance structure like this. So now N negative, P positive. Rather than drawing, that is writing the N double bond P, I have written here N minus P plus. So this negative charge, it can act as nucleophile to some electrophile, right? So suppose I am saying C double bond O, which is the electrophile. So it can attack this C double bond O. So in this way, we can get Aja-Wittig reaction. So you can find some similarity with Wittig reaction, but with different types of halide. So that is, it is Aja halide. So the name of the reaction is Aja halide. Then if you take some carboxylic acid, you will end up with amide. And also remember, this type of reaction can also be intramolecular. Suppose this carbonyl group or the acid group, it is already part of the molecule. Suppose it is present in this R part. So in that case, what will happen? There will be intramolecular reaction. You can also take epoxide and you will end up with aziridine. Then with CO2, it will be isocyanate. With CS2, isothiocyanate. So these are the different possibilities or you can say variation of Staudinger reaction by using versatile electrophiles. Okay. Next we will see mechanism for imine and aziridine formation. So in the previous slide, that different reactions that you have seen, out of that I have chosen two so that you can understand the mechanism, what is actually going on. So here I have taken this acetone, which is a ketone, and I have drawn this iminophosphorant with negative charge over nitrogen, positive charge over PPH3. So this negative charge, it can attack here. There will be negative charge over oxygen. This negative charge, it can attack this P plus, and finally there will be 4-member ring formation. And the next step, as we know, there will be P double bond O and CN double bond. So this is the imine that you are getting. If you want to reduce it, you can do reduction. And in that case, you will end up with NHR. So this will be, this is a method for the formation of secondary amine, right? For imine reduction, you can use NaBH3CN. Then we will see another mechanism which is for aziridine formation. So in aziridine formation, we have taken epoxide. So this negative charge, if it is attacking here, CO bond is broken. Now when CN bond is broken, then there will be that is, this carbon oxygen bond is broken, and this nitrogen and this carbon, there will be a bond, right? Now this negative charge, it can attack this P plus, and ultimately there will be OP bond formation. And if you are having any trouble to understand, just put some numbers. So suppose I am putting here 1, 2, 3, 4, 5. So here 1 and 5, that will be connected. This is 2, this is 3, this is 4. So if you put number, it will help you to understand the mechanism. And finally there will be OP bond formation. So OP bond formation, and this NP bond will be broken and 2-4 connection will be there. So as if it is 3, it is 2 where R prime is present, and nitrogen is 4, and 1 and 5 like this. Okay. So in this way we can get aziridine. Next we will see some examples and synthetic application. So the first reaction, as you are seeing here, retention of stereochemistry. So stereochemistry is retained. That is possible in this reaction. So this chiral center is not disturbed. From N3, which is below the plane, we are getting N double bond PPH3, and finally after hydrolysis there will be a primary amine, stereochemistry intact, and this is the byproduct. Next example, you can see how the double bond is intact even after doing this reaction. So this is also that is, you can say, synthetic application. Then heterocycle formation. Here we have this azide, right? And this C double bond O, that is a ketone, it is already part of the group, right? So when you treat it with PPH3, first, as we know, N double bond PPH3, and finally this 5 position and 1 position, this will be the connection point, and PPH3 will be PPH3PO, that will be removed as a byproduct. Now if you simply look at this product and the as if it seems it is easy to remember why I am saying so, as if you put C double bond O and NH2 and if you see remove water, and this is a imine formation, but remember it is not going through NH2 group formation because you are not using water. As we have seen usually in Staudinger reaction after PPHT we do hydrolysis, but here no water is mentioned. That means once this N double bond PPHT is formed iminophosphorant, then there will be attack with this C double bond O. So no NH2 will be formed. So it is actually not happening. Why I have just drawn it, so that you can remember how final product you will have. So it is just like if you have double bond O or NH2, but it is not going through NH2. So 3 examples here we have seen. 2 more examples we will see. Lactam formation. So suppose you have N3 group and CO2H group both in the same molecule. So when you are treating it with PPHT, first step as we know N double bond PPHT iminophosphorant, and from the numbers you can understand this COOH, here we have this C double bond OH. So here N and 6, this will be the connection point, and triphenyl phosphine that will be removed as byproduct. Another important application, which is suppose you have epoxide and you are treating it with, in aqueous medium you are treating it with sodium azide. So this N3 minus, it will attack here and this CO bond will be broken. In the medium you have water, so OH will be formed. These 2 groups, they will be trans to each other. Next, as we know, when we treat PPHT and nitrogen is removed, you are getting N double bond PPHT. Now this oxygen, it will attack here, there will be 5-member ring formation. So suppose this is 1, 2, 3, 4, 5. So this is 1, 2, 3, 4, 5. And finally there will be PO bond formation, and as if this PN bond will be broken. So there will be 4 and 2, this will be now connected. So this is 3, this is 2, this is 4, and this is 1, this is 5. So I am just putting numbers so that you can understand how the mechanism is going on. So we are getting aziridine starting from epoxide. Now we will discuss 2 problems from CSIR-NET where you can see the application of this Staudinger reaction. So here we have 6-member ring where you have double bond and OH. So this is allylic alcohol. Look at the reagents. The first reagent is MCPBA. So if I am writing this in this way, that is chair form, this isopropyl group, we have to keep it in equatorial, and these 2 positions are 1, 3, it is cis, so OH will be equatorial. Now here this in the same site there will be epoxide formation because it is allylic alcohol, we are using NCPBA. So if you are drawing without chair formation, if you draw, the epoxide will be like this below the plane, that is in the same site. So in this case the oxide will be epoxide will be like this. In the second step you are using NaN3. Now this N3 minus, it will attack here and there will be OH, that is CO bond will be broken. So this will be N3, sorry, it will be basically above the plane. So rest of the position there is no change. This is N3. Now I will not draw rest of the part because this same mechanism we have already seen, right? So third reagent is PPHT, and see here we are not using any water. No water is mentioned. So in the next step what will happen, this N3, from this N3 nitrogen will be removed and you will get PPH3 and rest of the part as it is. And as we know, this oxygen, it will attack this phosphorus, and rest of the mechanism how it is going on, that we have already seen. So I am just jumping some of the steps, but final the aziridine that you will get, it will be above the plane. So though we have to choose between any of these 2, not the other 2 options, but whether this aziridine is above the plane or below the plane, if that question arises, it will be above the plane. Okay, so that is why we will choose the second option as the correct option. This question is also from CSIR-NET. Now see, this is very easy. First reagent PPHT. That means just focus on this part. this part will not be disturbed, it will remain as R. So suppose if this is R group, rest of the part if you CHO. So we have total 4 CH2 groups. Sorry, I have missed. So total 4 CH2 groups, and from N3 there will be formation of iminophosphorate, and rest of the part, as we know, it is intramolecular. That means within the molecule you already have C double bond O, that is aldehyde, right? So that is why there will be ring formation, and rest of the part there will be there will be this group. So suppose the group I am writing it as R group. So here, as water is not present, there will be no formation of NH2. But what is the connection point? As we know, that is considering this nitrogen, there will be 7-member ring formation. 1, 2, 3, 4, 5, 6, 7. So this is 1, 2, 3, 4, 5, 6, 7. So this type of mechanism we have already seen how intramolecular reaction is possible. That means this part is remaining intact. See, this is actually the correct option. This part is the R group which is remaining intact. Now when there will be NC, first there will be NC double bond formation. But as you are using this reagent in the second step, which is very selective for C double bond N reduction, so that is why ultimately the C double bond N, that is the imine, that will be converted to that is, it will be reduced. So this option will be the correct option, right? And finally we will see 2 examples from recent research paper. So here we have very complex structure, but you just have to focus on this part. See, focus on this part. Though here step jump is there, because once the NH2 group is there, after that there is Bock protection. So N3 first it will be converted to NH2. And here I have already mentioned the reference. So if you are interested, you can check the details in this reference. Then one more example, that is also from JAX. Both are from JAX. And here we have N3 group, and this N3 group is converted to NH2. Here we have to, that is, this part is protected. So when R is equal to H, that means it is OH, then it is 29, then it is converted to, that is, it is protected, and then the reaction is done, PP3H2. So here water is used, so we are getting primary amine. So that's all for this video. I hope you will get some clarity on Staudinger reaction, and thanks for your precious time.